Okay.
Here in America, we should say math.
So remind me, what is it percent yield mean?
It is the percent amounts of each product in a molecule.
Okay. Go.
I don't know.
I feel like you got lost somewhere along the way.
In a compound.
It's how each element is in the compound.
No, not percent composition.
Oh, I'm
That's
I
percent
don't
composition.
know.
Wait, it's how much you can actually get out of the
Oh,
reaction.
yeah. If
How
you
much
add
of the theoretical yield actually comes out of a reaction?
There we go. What percent?
It's all
Thomas said that
four.
exact thing. Okay, percent yield gives us a relationship as to how much did we actually produce in comparison to how much did we expect to produce. So, what industry do you think yields are really important?
Business.
Okay, yeah.
Chemist.
Manufacturing, agriculture, right? All of those things are ones in which you...
Baking.
Cooking.
How's your baking yields change? You know how many cookies you're
In
making.
my life.
Yeah, what if the chef guy's like, I need 12
Chef
cookies
guy.
in
Are you
2
assuming it's a
hours?
guy?
Okay, so percent yield is going to give us a relationship as to what did we expect to produce from our reaction versus what did we actually produce in our reaction, okay? So it's what's expected. We're going to start looking at the ratio between theoretical yields and actual yields. Theoretical yields and actual yields. All right, let's talk about the equation here. I didn't even put the equation on this slide. Does anyone remember what the equation is for percent yield? Percent yield equals...
Theoretical over actual. Actual over theoretical.
Actual over theoretical, right? If I'm trying to find the percent of something, I always take the part divided by the whole, right? Theoretical is what we thought should happen. Okay, where does the theoretical yield always come from? It always comes from the t-chart. This actual yield will either be given to you in the problem or it will be what you actually get when you do the lab, right? You would do the lab and you would weigh out your yield, but it's what you actually get. So actual yield is either given to you in the problem or you are finding it in the actual experiment in the lab. And then the theoretical yield always, always, always comes from your T-chart.
What does that 1% stand for?
Percent yield. Percent yield. Okay, percent yield. So we would say if we expected 10 grams, yet we only were able to achieve a yield of 7.5 grams, our percent yield would be 75%. Right? We only got out 75% of what we were supposed to get out.
And like if the actual is so much more, you get like
Right. That would be a red flag if we get a yield higher than 100%.
That means that we did something wrong.
Most likely. Yes.
Or it's just a magician.
All right, let's try one here. How many grams of water will be formed if 36.5 grams of oxygen are used? I will tell you that percent yield problems usually have to end up dealing with grams. You don't find percent of moles. Okay, we find percent of grams. So we're going to take things all the way to grams when we have a percent yield problem. This one asks us specifically about water and oxygen. So we're looking at that relationship here. So we're going to have to do a stoichiometry problem first to determine which of our yields. Like which one is this right here? Is this the actual or the theoretical?
Actual.
That's the actual. So that means we need to find the theoretical yield of water. Right? That's the first goal. Does that part make sense? We need to first find the theoretical yield of water. That's got to come from a T-chart. So we start with what we know. And remember, look, it's not just O, it's O2. Okay, because what is that considered? O2 is one of what type of a molecule?
It is a
Starts with a D. Diatomic. Yep, diatomic. Okay, so we'll go grams of O2 to moles of O2. Moles of O2 to moles of water. And then we need to take this all the way to grams. Moles of water to grams of water. What are the other diatomic molecules?
I have it.
Bromine.
Yeah. Bromine.
Bromine.
Wait, it makes
Oh,
the
no.
same.
Where's your periodic table?
I wrote it down. I just wanted to see the
Nitrogen,
memory.
oxygen, fluorine,
Chlorine,
bromide, iron,
And hydrogen.
Very good, right? It makes the 7
plus
and then hydrogen. Yep, very good.
hidden.
All right, so here we go. I'm going to put in my numbers here. 1 mole of oxygen weighs 32 grams. What's this step right here called?
mole ratio.
Mole ratio, good. And do moles get the 1 in mole ratio? No, not in that step. So moles of water would be 3, moles of oxygen would be 6, and then 1 mole of water weighs 18 grams. So I'm going to go ahead and do the math, right? I need your calculators out if you don't have those out yet. Multiply across the whole top, divide by the whole bottom.
I still need to figure
My
out how to
calculator's in my pocket.
store.
I kept it in my pocket. Yeah, I was trying to fool us right then. Use that search.
I got about 10.3.
Yeah.
Okay, I rounded it to 10.3 because I started with 3 sig figs. Right, that's where I chose to round that.
9. That is not what I got. Let's try this.
All right, so now if I'm trying to look at percent yield, I'm going to come up here and give some room in the corner here. I'm trying to find the percent, which means I'm going to take the actual, 7.95.
Wait.
It kind of looks like a 1, doesn't it? It's a 7. It's just the font.
Oh, that's why.
7.95 over 10.3.
That's fine.
77.2%.
Good. Right, it comes out as a decimal, but we're going to go ahead and multiply that times 100 to get it into a percentage.
Oh my gosh,
And we get about 77%. Very good. Okay, so if I'm looking at this problem, it tells me my starting amount.
this is
It tells you
the.
everything you need to go.
Right, tells me everything. I got my percent yield. What's my final answer gonna be like in terms of, am I looking for my theoretical yield? Am I looking for my actual yield?
Actual, because you're going to find theoretical.
Right, I'm gonna look for my actual yield of water. That's really the goal. Because it tells me my percent yield, we're looking for the actual yield of water. Okay, so I'm gonna give you a couple minutes head start, and then I'll put it up here on the board. Once we get here, this is our theoretical yield. Did you remember to put your percent back into a decimal when you get to this point?
And then you get 6.8.
Because if you don't, your actual yield would have put you way over your theoretical yield, which wouldn't have made sense, right? So we got to put that into a decimal. 17.5 times 0.39 gives me 6.83.
Do you have to multiply them together?
Right, because I want actual by itself, so I'm going to move 17. I'm going to move 17.5 over. Yep.
I don't know words, so I use random words.
20.7 grams of calcium carbonate produces 6.81 grams of calcium oxide. Is this our actual or our theoretical yield?
Theoretical.
We need to. That's the actual. We need to find
Right.
the theoretical.
We would find the theoretical, then calculate the percent yield. So we'd start with 20.7. We would find our grams of
Because if it was the theoretical
calcium oxide.
we wouldn't be able to find the percent yield
right.
or the actual.
All right.
So,
Come on.
All right, let's look at limiting reactants.
building reactants.
All right, limiting reactants. Remember we skipped a couple. We skipped ahead a little bit here. Okay, so we're going to limiting reactants.
Yeah.
Limiting reactants, we need to think about them as kind of recipes, right? We think about chemical reactions as recipes. So when I go to make a recipe that calls for 3 cups of flour and 2 cups of sugar, but I realize I only have 2 cups of flour, can I make the whole recipe? No.
You gotta make like 2/3.
That's right. That's right. I would have to make 2/3 of it, or I have to make whatever. I can't make the whole recipe. So in that situation, which one of my ingredients would be limiting my production?
The one you don't have enough of.
That's right, the flour, right? I needed 3 cups, but I only had 2 cups. That's limiting my production. The same thing happens in chemical reactions, okay? When we start looking at questions that give us multiple starting amounts, that's a clue for us that we're going to be doing a limiting reactant problem. Okay, we do the stoichiometry to predict how much could we produce based on these starting amounts. Okay, so let's look at this. How much NH3 could be made if 2 moles of NH2 were reacted with 3 moles of H2.
Is it still?
It'd still be the same, right?
Right, so let's just say if I had 2 moles of this and 3 moles of this, how much of my product could I make?
2.
Because your H is.
You would need more hydrogen.
I could still only make 2 moles of ammonia because even though I've got twice as much nitrogen gas as I need, I've got exactly how much hydrogen gas I need.
And you just have leftover.
So I would have leftover nitrogen. Right. I'd use, how many moles of nitrogen would I use if I had 3 moles here?
1.
I would use 1 and I'd have 1 left over. Right? 1 left over. All right.
Well, yeah, obviously I didn't remember.
Yeah. Obviously you guys feel really confident about it. Okay. This is the clue for us that we're doing a limiting reactant problem is when we're given two starting amounts. If we're given 2 starting amounts, we can't just automatically assume what our limiting reactant is because things have different molar masses, different mole ratios, and it's hard to make that assumption just based on I've got less sulfur, so like it's going to be my limiting reactant. That's not the case always, okay? So this equation looks like it's balanced. We're going to go ahead and start looking at our problem here. What's the maximum mass of copper sulfide that can be formed? Okay, the maximum mass of copper sulfide that can be formed. So remember limiting reactants is when we start to like go into T-chart city here, right? We've got lots of T-charts in our problems. Okay, so we do for sure these ones, we do the problem twice essentially. One from 82 grams of carbon to our product and one from 25 grams of sulfur to our product. Right? In this case, we only have 1 product. So we didn't have to choose. But when we have multiple products, I'll show you how we go about the process of choosing. Right? They got to go to the same one. They always have to go to the same one. But we'll go from there. So let's go ahead and try this one. Yeah, if you're allowed a choice, I would choose the one with the easier molar mass. Grams of copper to moles of copper. Do you guys have enough room on your slides to do these?
I'm going to get really small.
Probably.
Okay.
We're gonna make it tiny.
We're gonna find out. If need be, I can go outside the slides.
I thought you were just gonna stop it.
Outside.
Yeah, I'll go inside.
I was like,
I can be.
I will leave the class.
It's okay. I'll do that for you. I'll go with you.
Copper's molar mass.
63.
Thank you. I should have known that. 63.5.
Hannah said first.
Okay.
63.5 times 2 plus 32. 159 here for the other one.
Whoa.
I think. No?
Whoa.
Yes, I think. But
You're most likely right.
You're really fast.
You're just really zooming.
Sorry. Oh, I forgot to make this small enough.
Yeah, that made me really do be adding the molar mass though.
102.7 grams of Cu2S. Okay, now we do another chart from our other starting amount. 25 grams of sulfur.
Wait, are we going to do another teacher?
No.
I mean, after.
So grams of sulfur to 1 mole of sulfur.
32.
That's not
Thank
how
you.
Right.
Moles of sulfur to
Me.
moles of copper sulfide. 1 to 1 here.
We can just eat.
You could skip it if you feel so inclined.
Yeah,
If you
James.
just, want to skip
Why was that a
ahead.
yeah, James moment?
Okay?
You don't
The
have
good thing
to.
about these is that you'll have the same molar mass, right? You already calculated molar mass for copper sulfide, so you don't have to calculate that again.
James moment.
Okay, so we'll multiply across the whole top, divide by the whole bottom.
124.2.
Good. 124.2.
Therefore, the limiting reactant.
Okay, so yeah, which one is it? Which one's limiting?
Mr.
5.
Mustard is the.
So,
Our limiting reactant. Do I just do this?
I thought it was copper.
No.
Do I this? Limiting reactant is this?
Yeah.
No.
No, because what is copper sulfide? It's the product. It's not the one that's limiting our reaction. Our limiting reactant, it does come from the smaller amount of product formed, but it's this, right? Limiting reactant is copper, not copper sulfide. That's a really common kind of just quick mistake that you make. You go, oh, here's our limiting reactant, right? And I know what you're thinking, but it's not quite correct, okay? So we have to be careful with that. The second thing I want you to think about, The second thing I want you to think about is though it says, what's the maximum amount of copper sulfide can be formed? So why did we choose 102 instead of 107? Or sort of 124?
Because you can't make any more because you don't have enough copper.
Yeah.
Bingo, right? Bingo. Okay, we would never get to the point where we could make 124.2 grams of copper sulfide because we would run out of copper first, right? That's really important part of it. So the answers to our question, what's the maximum amount of copper sulfide can be formed? This is it right here. And technically, this question didn't even ask what is the limiting reactant, right? We had to put those principles into play to solve the question, but it didn't even really ask what is the limiting reactant. We did the work for it, but all you're really answering here is that guy. Okay? Does that make sense?
Yes.
Okay. Try this one on your own, and then we're going to add some things to it. In on one other little secret here. In this question, anywhere, does it ask for the mass of the product?
No.
So, realistically, I could take both of these to just moles of H2.
You're right. You're right about that.
Right? I could take both of them to moles instead of going all the way to grams if I wanted to, because all it's asking for is the limiting reactant. So I could stop at moles as long as it doesn't ask me anything else about grams or about percent yield. Right? So in this case, since it only asked me for limiting reactant, I got to go to whatever product I wanted, number one. Second of all, I could stop at moles of that product. I don't have to go all the way to grams. So I didn't. If I did go all the way to grams with both of these, I would have just taken them, times 2 grams times 2 grams, right? It would have given me the same ratio. I just saved myself some time. So this case is, do I just go like this and go limiting reactant right there? No. My limiting reactant is
Can I?
HCl.
Wait, so if you
Put-
did do the extra work for 2, you would get different numbers?
Different numbers, but the same limiting reactant,
Would
right?
you kind of wrong
Nope.
on that?
Nope. Because all I'm looking for there is that answer. You know what I'm saying? Is limiting reactant.
Yeah, I think I might just
Can I?
Right here it says ethylene, which is C2H4, combust with oxygen. So what does that have to be? Okay, plus O2. How many grams of carbon dioxide are formed? That means carbon dioxide has to be a product. What's my other product of a combustion reaction? Water. Bless you. Combustion reactions always start with a hydrocarbon and oxygen, and they always produce carbon dioxide and water. Okay, so now we need to balance that from there.
You need to multiply that by 2.
Oh, not 0, sorry. 1, 2, 2, 2.
I think you're going to need more oxygens than that.
Wait, because...
3.
Oh, wait.
Let's
Okay.
balance
Yeah,
right
it's
now.
1, 3, 2, 2.
Wait. Am I? Yes, I am.
1, 3, 2, 2.
Don't doubt your.
So this one says how many grams of carbon dioxide can be formed. So this one, it tells me my product I need to go to, and it tells me I need to go all the way to grams. So let's go ahead and do that.
Thanks.
All right, get started. C2H4.
You can do it.
If I don't do it, I die.
I believe in you.
I don't.
C
Do we need?
12. So that's
Yeah, we gotta go on over grams.
Yep, because it asks specifically how many grams of carbon dioxide.
How did you write that?
yeah.
Practice.
Okay, now our question's going to go on to extend the question now to look at something called excess reactant. If I say excess, what's that mean?
How much?
Left over. How much is left over? So this is what the next slide says. How much, does it just say how much excess reactant is left over? Okay, so first we had to determine what's the next slide say?
What is the mass?
What is the mass of the excess reactant? Okay, so which one of our reactants is the excess?
C2H4.
C2H4 is our excess. So here's what we need to look at. Listen. We need to now do another chart from our limiting reactant to C2H4 to see if I use up all 3.25 grams, how much C2H4 would I use? Okay, that's what that relationship shows us. So let's go do that. I'm going to not move the slide forward. I'm just going to erase what I got here. So 3.25 grams of O2, and we're going to go to grams of C2H4.
So is the answer how much you used or how much is left?
It's going to be how much is left after you use it. So we're going to do a subtraction at the end also. Okay, so I'll show you what that looks like.
Okay.
It's really important that we fully understand what this T-chart is representing. So I will talk through that after we kind of get done here. But moles of O2 to moles of C2H4, and then moles of C2H4 to grams of C2H4.
The other one that's reacting.
Was the mole ratio here 1 to 3? Because I erased my... Okay, and then that one would be 28 grams.
I was like, that's the wrong one, man.
I'm on the next slide. Sorry, I just didn't move it forward. Okay, so let's really make sure we understand what this T-chart represents. We know that because O2 is the limiting reactant, in our reaction, we're going to use up all 3.25 grams of oxygen. Do we agree with that part? Yes. That's what it means to be the limiting reactant. All of it's going to get used up, and then the reaction stops. So this T-chart tells me if I use up all 3.25 grams of O2, how many grams of C2H4 does that require? That's what this chart is telling us. We need to have, let's do the math, 3.25. What is it?
3.95.
Y'all are too much for me.
Yeah, stop.
I didn't get, I got,
I got 0.95.
That's what I got. Okay. I got 0.95 grams of C2H4 that was used.
Where you at?
0.95 grams of C2H4 that was used. Okay, this tells us that by using up all 3.25 grams of O2, I would need to have 0.95 grams of C2H4.
And then you subtract that from the total?
That's right. We started with 4.95 grams of C2H4. So I'll come take 4.95 minus 0.95 grams used. Yes, and that gives me 4 grams left over. Right, we did that one without our calculator. Great. You would need to take this particular T-chart to whatever unit your excess reactant started in. So if this was given to us starting in moles, we could stop that after moles and then do the subtraction. You know what I'm saying? Okay, how do we feel about that?
So good.
So
5 out of 10.
good.
Good.